Hello, everybody. Welcome to our webinar on Snowflake, BigQuery, or ClickHouse. We'll be talking about pro tricks to build cost-efficient analytics for any business. My name is Robert Hodges, and I'm CEO of Altinity. I'm joined here today by Chiara Toselli, our head of marketing. So it is a pleasure to be able to talk about this topic. Let me just give a little bit more in the way of, before I dive into the introductions, let me tell you a couple things about this webinar that will help you enjoy it more. First of all, it's being recorded. So we will send out the link to the recording as well as these slides within 24 hours of the end of the webinar, hopefully sooner. So you don't have to take furious notes. They're going to be available to you in your email, also on the Altinity website. Second thing, we have time for questions. You can go ahead and post them in the question and answer box, which is included in the little control panel that Zoom gives you. You can also put them in the webinar chat. We can answer them there, and we'll take them if they're relevant to the slide that I'm on. I'll just take them right then and there. Otherwise, we have time at the end to talk about them. Okay, let's dive in and do a little bit more on the introduction. So once again, my name is Robert Hodges. My day job is I run Altinity, but I've been working on databases for, it says here 30 plus years. It's actually 40 this year. It's been a while. I've been worked on about 20 different database types. I've also worked extensively in virtualization. I was at VMware for a while, and that's in fact where I began to learn how to use Kubernetes, which is something we're going to talk about later in this presentation. I'm backed up by an amazing engineering team. About 2/3 of our company of 45 people has engineering background, and they are database geeks, just like me, except that many of them have even deeper experience in database and applications. As a company, we are enterprise providers for ClickHouse, an outstanding real-time analytic database. It's open source. Among our offerings, we have Altinity.cloud, which is a cloud version of ClickHouse. We also have ClickHouse run in the cloud. We also do Altinity stable builds, which are builds of ClickHouse designed for enterprise users. They have 3 years of support. They're certified for production use, so on and so forth. And another thing that we do, and some of you on this call may already be aware of this, we're the authors of the Altinity Kubernetes operator for ClickHouse, known as the ClickHouse operator for short. We've actually been working on getting ClickHouse to work cloud native for almost 5 years at this point. So that's something where we have deep experience on, and you'll see we'll be sharing some of the things that we've learned in that process today. Excuse me. Okay, let's dive in. So in the first part, I'd like to jump in and talk a little bit about analytic database and explain how the cost models work, particularly when you're running them in the cloud. So analytic databases in the cloud got started in 2013 with Amazon Redshift, and it was a groundbreaking product. Basically, what Amazon did was they took a data warehouse, which was an existing on-prem installed data warehouse. They put it in the Amazon cloud and basically allowed you with a credit card to start this data warehouse in 20 minutes or less. This was an amazing advance. It's sort of like in the same way that we don't fully appreciate how great COBOL was because what came before it was assembler. It's easy to forget just how great Redshift was because prior to Redshift, it could take up to 6 months to install a data warehouse because you had to, make a deal with a vendor. You had to go get the hardware. You had to get the hardware stuck in a rack. You had to get everything configured. And by the time all of that stuff worked through dealing with procurement, fighting with your managers, it was 6 months. So this was a huge advance. And within a few years, there were several excellent data warehouses available in the cloud, including BigQuery, Snowflake, Redshift, and more recently, cloud services that operate Snowflake. So to get to the cloud efficiency question, it's kind of useful to talk about how most developers particularly learn about cost efficiency. If you're running BigQuery, it's easy. You can run a query that costs you hundreds or even thousands of dollars. This is an example that appeared in in Twitter earlier this year, and it's not unique by any means. So this brings up a big question. Well, $300 for one SQL query, that seems like a lot. What is going on down there? And that's what we're going to do in this section of the talk. We're going to talk about how these data warehouses work in, sort of at a high level, and how the pricing works. So let's start with Snowflake. And we're not going to show you architecture yet. We're actually just going to talk about the business. This turns out to be a surprisingly useful way to understand what it really costs to operate these database systems in the cloud, and from that you can infer what the markup is on that you're being charged. So for Snowflake, it's easy. It's a public company, and we can just go look at their financial results. So, for example, the results reported in the 31st of January this year showed a total revenue of $2 billion, of which the cost of revenue, sometimes called the cost of goods sold, was about $717 million. So that's an interesting number, because that is the cost in a P&L statement, a profit and loss statement. That's how much it cost Snowflake to deliver their service. So what that means is the cost for running their cloud is hidden in there. So if you just do the math, that's about a third, a little over a third. So what that means is if all of that were cloud cost and nothing more, then that would mean that they are marking up when they charge you and collect revenue, they're roughly marking things up by about 3 times. Now, in fact, the actual delivery costs for for a service like Snowflake are much wider, and don't just include running VMs and allocating storage in places like Amazon. They include things like paying SREs. They include things like hiring other services that are necessary to work, all kinds of things that are necessary to make the whole service work completely. So in fact, the markup on their cost is about 5x, something in that on average. That's a useful number to keep in mind, because you can then use it as kind of a benchmark for, hey, is something really expensive or not? If it's greater than 5x, hey, it's bigger than the average Snowflake market, roughly. If it's less than 5x, then it's less. So it's a cheaper offering. Let's now look at the Snowflake costs and figure out, what they really look like in terms of the deal you're getting when you run their database. So Snowflake uses something called a virtual data warehouse. It's a very innovative architecture. Stores the data in S3 object storage. They were, I believe, the first ones really to operate this model at scale. And then what happens is, when you want to work on your data and run SQL queries, you create what are called virtual data warehouses. And you can have a couple of them running together. They are basically operated by, or you pay for this using credits. And a credit you can think of as mapping to a host somewhere that has pulled in data from object storage and is processing SQL queries on it. So we don't know necessarily what these VMs are, but you know that if you go look at the pricing list, their on-demand pricing ranges from about $2 to $4 an hour for one of these VMs. Now, this would be the end of the cost analysis, except that a little while ago there was a bug in Snowflake that if you issued a query that failed in the right way, it would print out the kind of VM that they were actually running. So it turns out that, at least in some cases, these things which I've marked credit and represent VMs actually map to C5D2X large instances, which cost about, currently they're 8 vCPUs, and they cost you about 38 cents an hour to run. So that's an interesting number. Now we know what the object storage is, because Snowflake is storing it, and we can see that Snowflake charges between $23 to $40 per terabyte per month, which interestingly is not that different from the Amazon on-demand S3 costs as well. So they don't really mark up the object storage very much at all. What they do mark up is actually the virtual data warehouse. And we can see from this that if you're going to be offering cheap storage, you got to make it up somewhere else. So what Snowflake does is it makes it up in compute, which can be anywhere from 5 to 10x more expensive than the corresponding hosts. So that's basically gives you an idea of how the Snowflake virtual data warehouse model works. Let's have a look at another one, which is quite different, and that's BigQuery. So BigQuery is the other really large cloud database or analytics service. And BigQuery has a number of pricing models, but I'm just going to focus on one, which is what's called the serverless or on-demand query model. And the way that this works is when you're using this model, you can store the data. You store the data on distributed storage. It's actually not object storage. It's a different proprietary system, at least up until recently, and it's charged at about object storage rates. So you can see these prices per gigabyte if you go compare them to to the prices that you get if you allocate object storage. It's pretty comparable. One important thing to notice is these prices are not for compressed storage. That's a big thing. We'll talk about that in a minute. But the basic idea is you've got your data stored out here, and when you run a query, BigQuery will allocate some number of compute nodes, whatever it thinks is the right number. You don't know, because what it's going to do and what's going to appear on your bill is it's going to charge you $6.25 for every terabyte of data that it scans in answering your query. So it's pretty easy to see from this how you would actually, how somebody could run up a $300 bill. What you would have to do is just read enough terabytes of data out of this distributed storage, and you get a $300 bill. So that's going to be probably about something like 15 terabytes. If you have a large enough data set, this is not hard to do. And you can also see how this might actually expand up into thousands of dollars if your data set were large enough and your query were read enough of it. So how does this compare with actual cloud resources? Well, we could just pick a standard VM. This is N2D standard, 32 vCPUs. We can look at the cost of object storage, which, as I mentioned, is kind of comparable, except for the fact that it may be compressed or not, kind of comparable to what BigQuery is charging. You do have the block storage, the cloud block storage. That is pretty expensive on Google. It's about 17. Last time I looked, it was 17 cents per gigabyte per month. But the problem is these numbers don't really tell you anything. Depending on how your data is arranged, this could be anywhere from 10 times cheaper. BigQuery could be anywhere from 10 times cheaper to 10 times more expensive. So what's an example of how BigQuery could be cheaper? Well, if you only run the query once. With this N2D standard 32, that thing is sitting there until you turn it off. You're getting charged for it. And if you're keeping most of the storage on block storage, that is more expensive, and therefore you're paying more. On the other hand, if you run constantly, queries 24/7, which is the case for many analytic applications, it could be way more expensive. So you could end up spending vastly more on BigQuery. It's really hard to judge, and you actually have to look at your workload and decide how you're using it. Find out what your actual costs are. We'll compare this a little bit more in just a second. Let's talk about one final model. So it's pretty common in both of the models that I've described so far are use object storage, or in the case of BigQuery, something very like it. And but there is another model for operating databases in the cloud, and it was the one that was actually pioneered by Redshift when they first opened up 10 years ago. So I call it the buy the box model. And if you go and look at the pricing for and set up Redshift, you can still see this model 10 years later. Basically, what you do is you hire out a VM. They call it, for example, a DC2 8x large. It has attached block storage. As it turns out, it's SSD, and they'll charge you $4.80 an hour in Amazon US West 2. How does that compare to the actual costs? Well, luckily for us, we can sort of figure out what this VM is. It turns out that it is, unless things have changed, it's probably an i3 8x large VM, which is a one of the older instance types in Amazon, and it has local SSD. And here's an example of the pricing for that. That's now about that's going to be about $2.50 an hour, and has very comparable, as you can see, almost exactly the same amount of RAM. That's why it's pretty clear that it's either this VM or something very like it. How does that then compare in terms of markup? Well, Redshift is, in this particular case, is 92% costly, or more costly, but gives you 66% less storage. So you can get a better deal. But actually, it's interesting. The markup on Redshift is not super bad. It's always had a lower markup than, for example, Snowflake, which really dings you on compute. The reason being because they allow you to have this relatively cheap object storage. Now, we can improve on this model significantly. And in fact, to see how to do that, it's useful now to introduce ClickHouse. So ClickHouse is a popular open source real-time analytic database, as I mentioned above. Here's the basic architecture. So you can have two types of storage, but the key thing that you're going to have is ClickHouse servers, which are going to be connected to each other over a network. They can replicate. If you define a table in, you can define replicated tables, in which case if you add data to a table on one host, it will automatically replicate to the other. The storage is columnar, like all of the databases we're dealing with today. So that means the data is stored in arrays, that those compress well. They're also cheaper to query because you don't have to read as much storage. And when ClickHouse was originally developed, it could only store data in block storage, but it has since been improved to be able to store the data in S3 compatible object storage. So that is to say, any object storage which has an S3 API. It also includes a either Keeper, what's called ClickHouse Keeper, or Zookeeper. This is a cluster which is used to maintain consensus about the data that needs to be replicated between servers. So this is the database architecture. We can map this as a cloud service to something that I call modernized by the box. And so here on the left, you have your original Redshift architecture. On the right, we have a new version of it where instead of using, well, underneath what turns out to be i3 instances, we can use M6Is, which are a Intel-based, very fast. Clock speed is at least a third faster than the old i3s. And the other thing is it mounts the storage on EBS. So EBS is like a SAN-based storage, the elastic block storage. It's really versatile, and it turns out that if you with the newest versions on Amazon, what's called GP3 storage, you can control the bandwidth and the throughput. So if you dial it up to get a throughput of 1,000 megabytes per second, that together with this nice VM, which is roughly comparable to what you're running on Redshift, is going to run you about $2.64 an hour. So that's still about the same markup, but there's actually another thing about this that's really important, which is that by separating the storage and compute, you can now easily adjust the relative amount you spend on compute versus storage. And let me show you an example of this, because this is exactly what we do, right? What we've done in actually for years in Altinity.cloud when we manage ClickHouse. So by having separation of storage and compute at any time, you can change the CPUs that you are using, the VMs that you're using, and basically just remap them to the same storage. What that means is that depending on what you're doing, you can then scale your costs up and down just by changing the VM types. And in fact, this graph right here shows you the all-in on-demand cost for Altinity.cloud when it's running ClickHouse. You can see that the M6i, if we use that M6i 12x large, it's going to cost $6 an hour to operate, which is more expensive than Redshift. But what's important is that one, ClickHouse is really fast. Two, M6is are faster than the Redshifts. So in fact, when we deploy, we would probably recommend that you use smaller instance sizes, which means your costs are correspondingly lower. And you can of course adjust them, but this illustrates the kind of benefits you get from this separation of storage and compute. So these are three models for how you can host analytic databases in the cloud and the effect that they have on your costs. Let's do a quick comparison. So this wallet size table shows the different ways that these models compare to each other. So you have by the box, which gives you relatively cheap compute, but more expensive storage because you're using block storage. That's on average about 5 times more expensive than object storage. Whereas the Snowflake and BigQuery give you cheap storage, but ding you in other ways. So for example, in the Snowflake model we looked at, compute is relatively expensive, and up to 10x times what you would really pay for it yourself. BigQuery, the on-demand query model, can be extremely expensive if you have queries that scan a lot of data. I want to be totally clear, BigQuery also allows you to price it by compute. These are things called slots that you can reserve, and then you have a model which looks closer to Snowflake, so you can play around with it. But what that means is that if you look at these models and what they're most effective for, this by the box is really good for customer-facing analytics, where you have customers and you can't control what they're going to do, or when they're going to do it, or how often they're going to do it. Just having boxes means that you won't get cost overruns, whereas the virtual data warehouse model can be very expensive if you're doing complex, if you need to allocate storage to do complex queries. And BigQuery, of course, can be very expensive if you unexpectedly scan more data than you really wanted. And that's something that's difficult to control up front. So this gives you the coverage. Let's have a look at dig in a little deeper and sort of look at how you get the best deal for these cloud services. So it's worth, given that the Snowflake markup is so high, let's zero in a little bit on what value you're getting from Snowflake, because there's some things that are costly often are costly because you're getting something good, and Snowflake is very good. It's a general purpose database. In fact, this is one of the best things about it, that you can just put practically any analytic app on Snowflake and it's going to work. It might be more expensive than other models, but if you're operating across an entire company and you just want to pick one thing that'll work for everything, Snowflake is probably it. Because it has, and some of the other things on this slide illustrate that it can handle vastly different use cases. It has a very good SQL implementation, has great integration with tools. And in a nutshell, one of the things about Snowflake that's really good is people who've worked with BI in the past on things like Teradata or Vertica can convert to Snowflake, and without having to understand too much about what's going on underneath, they can build applications that work and get out on time. What it doesn't do is the following. So it doesn't keep the data in your account. So if you care about that, it doesn't help minimize the cost, especially for these compute intensive 24/7 or real-time analytics. It's not a very particularly good solution for tenant facing. Like if you have like thousands of tenants and you have uh, sort of tenant facing dashboards, Snowflake is not necessarily a good uh, one for that. And then finally, it's completely proprietary. So if you want to, if you want to get off it, you're talking months at the very least to port it to a different implementation. That said, a lot of people choose Snowflake. And again, a classic example, a company wants to make one choice that works across the entire company. Snowflake is a good choice. So if you're going to use Snowflake or any other cloud service, the question is, what can you do to get a better price? So, and here's 6 tips. These are based on, we spend a lot of time thinking about pricing because we're offering a service ourselves, but key things to look for. Decoupled storage and compute. You don't want to buy into databases that can't scale up or down. And you can do it 2 ways. People tend to get fixated on object storage as the only way to scale compute. But in fact, block storage and VMs scale very, very well and turn out to be super well suited for many analytic applications, particularly 24/7 real-time analytics. Another thing is to be really careful to make sure that if you're charged for storage, that it's compressed. Snowflake compresses the storage, ClickHouse compresses the storage. BigQuery doesn't necessarily do it. It's called logical versus physical. So you want to double check to, and since for columnar databases, you can often get 90% compression. So you really want to make sure that you're getting this. Another thing is if you're spending a lot of money per month, you shouldn't even have to ask for a discount. Your vendor should give it to you. So that's something, if you're not getting it, ask for that. And speaking of discounts, look for price. If you're going to negotiate, look for price breaks that align with the vendor's discounts. Just to give one example, unless you're really big, it's kind of hard to get discounts on storage in the cloud, but compute is heavily discounted. So you can get discounts on Amazon VMs of 50% or more simply by prepaying. So your vendor can get that discount. And what that means is that if you do something that, for example, do a prepay, you can basically reduce that part of the cost. That could be a major savings, like, a third or more. And then finally, a classic thing is to buy on the cloud marketplace. So for example, the Amazon marketplace, and apply that price to your own commits. So that's an advantage of marketplaces. And even though it doesn't lower the cost, it lowers your overall cost because then it allows you to get, to meet your obligations to Amazon or Google or others so that you can get other types of discounts. So, and then the final question is, when's it a good deal? When is it cost efficient and works for your business? It really depends on your business. There's so many different reasons, but everything from, hey, I can actually afford it. Is it too much? Well, don't do it. You'll look for another solution. Maybe you don't really need analytics, or all the way down to the vendor pricing being in line with their revenue. I would just point to 2 things that I think of when I look at pricing for cloud services. One is that as your revenue grows, the cost of running analytics should scale at or less than your revenue growth. So because what you're seeking yourself as you build services is that your marginal cost of adding new users goes down over time. That's what makes SaaS applications work. If you have an analytic database that gets more expensive per customer as you add more customers, that's a problem. So do the math, figure out if that is the case. Another thing to look at is to see whether vendor pricing is in line with revenue. So you may have noticed when I showed you the Snowflake P&L for their yearly P&L, their pricing, in fact, didn't cover all their costs. Now, in the case of Snowflake, they're doing a lot of investment, so that will probably equal out just fine. But if somebody is charging way less than, for example, giving you something that's essentially at cost, that could be a big problem because they're really charging you, uh, less than they can truly afford. And at some point, gravity will reassert itself and the prices will change. Okay, that's cloud services. Let's think about what would happen if this wasn't if a cloud service wasn't a good deal. What are your options for doing it differently? And let's pick helps to pick a specific problem. So for example, let's say you're in Europe and you've decided that your destiny is to build a GDPR compliant replacement for Google Analytics. Lots of people are in fact doing this, including customers of Altinity. So this has a bunch of features, everything from analytic queries to data pipelines to visualization and consumption. We're going to build the core platform using open source. So first of all, let's do a reality check against Snowflake. Why don't we use Snowflake? Well, Snowflake has strengths, which we showed. In this particular case, it's nice that it's serverless. In other words, you don't have to worry too much about what's going on down there with the instances. It's all automated for you. And it has a UI with SQL editing and management and lots of tools on top of it. Those things are great. But a lot of the strengths of Snowflake don't really matter, like having standards compliant SQL. Yeah, that's nice, but you're not porting this and you're just building a specific application. That's not a particularly big deal. And in fact, the Snowflake weaknesses are vastly outweigh the benefits. So for example, just being able to keep the data in your own cloud account, that is necessary to allow you to efficiently meet GDPR. You're also paranoid you don't want data lock-in, and then of course there's other things in between. So Snowflake isn't the right solution. So what we're going to do is introduce an alternative. And what we see a lot of people doing in the marketplace is building what we call the modern analytic stack, which is based on Kubernetes. And the idea is you're going to build a custom platform which will deliver exactly the analytics that you need for your particular application. And the key things in this, when we see this go well, people use cloud native technology, specifically Kubernetes, which is very good for distributed applications. We see them using open source. We see them using infrastructure as code, so defining the whole stack as something that you can check in, for example, to GitLab or to GitHub, using GitOps to deploy it. So basically taking that checked in code and then blasting it out to one or more environments. And then finally, of course, operating, using Kubernetes and clouds as the runtime. So there's a pattern to these. They're kind of cookie cutter. This is a diagram that shows typical layering, but you have the GitOps, the CI/CD, sort of the continuous integration, continuous delivery, and Kubernetes sort of as the base assumptions. And we'll show you specifics on this. And then you have layers within it. So you have a management layer that covers things like operators. We'll talk about those in a second. You have storage, which is your database engines, orchestration, which is your data pipelines, change data capture, ETL and reverse ETL, and then finally consumption, BI tools, your own applications and APIs. These tend to be glommed in together, and I've sort of listed them in the order of their dependencies. So how do we actually start building this platform? Because what we're going to do is we want to actually fill in the layers so that we can get something that's deployable. So first thing to do is choose a Kubernetes distribution. And for this, far and away the best practice is to go ahead and use managed Kubernetes. If you got to run Kubernetes, let somebody else run it for you. You've heard that Kubernetes is complicated. That is true. But it's mostly complicated to run. Actually building applications on it is not anywhere near as hard. And the thing about the managed Kubernetes that's available from the major public clouds is it's amazingly cheap. In fact, in a truly amazing coincidence, they all charge 10 cents an hour. For example, Amazon EKS, that works out to about $72 a month. This is, you'd be crazy to, you'd really be kind of nuts to not to do this. So we use this in our own cloud. We run hundreds of clusters and we use managed Kubernetes. So that's the first thing. You just pick one, because what we're going to describe here will work on any of them. Second is to pick the right open source analytic database. There are many options out there, and they are less general purpose than Snowflake or BigQuery. So in our particular case, ClickHouse is absolutely the right choice because it does real-time analytics. In fact, web analytics was the original use case for ClickHouse when it was developed 15 or so years ago. The next thing is, if you're running databases in Kubernetes, you want to use an operator to manage it. And in the case of ClickHouse, there's a really good one, which is the Altinity operator, also known as the ClickHouse operator for short. And the way that operators work is they define what's called a custom resource definition, which makes the database a new type of resource in Kubernetes that you can just apply. And there's a program called kubectl. If you've used Kubernetes, you're very familiar with it. You just apply a piece of YAML that has a definition of the database in a custom format, but very compact, sort of 12 to 24 inches of YAML that gets fed into Kubernetes. Kubernetes will recognize, hey, this is a resource that the Altinity ClickHouse operator needs to manage. It'll hand it over, and then the operator will adjust reality. It will define new resources in Kubernetes, which will make that database turn into reality. So that's the third thing. Fourth thing is you need to choose your observability platform. There are many of these available, but one that's particularly powerful in Kubernetes is to use Prometheus. That's virtually universal among for doing analytics. It will collect it's a time series database. It will collect your data out of things like the Altinity operator, which will automatically export metrics, and then you use Grafana to build dashboards. And so Grafana is very powerful for operational dashboards that allows you to do, for example, to zoom in, look at particular series, to change the time scale. It's super useful. It has great plugins for both the Altinity ClickHouse DB, or for the ClickHouse. We maintain that. It has about 11 million downloads. It's used in thousands of installations. There's also a very good plugin, of course, for Prometheus. And then the final thing is to pick a GitOps implementation. So what you want to be able to do is check in the code that defines this stack, and then be able to apply it to Kubernetes clusters in different locations. There are several ways to do this, but one that we've seen used very successfully, and we use ourselves, is Argo CD. So, and what Argo CD does is it will take projects that are located in GitHub, and they can define the different services that we're going to run in Kubernetes in a variety of ways. A simple one is you just have a YAML file, which we call a manifest. There's also a project in Kubernetes called Customize, which allows you to tailor the manifest depending on which environment they're going to. And finally, the Helm charts, which are kind of like apt install or sort of Debian packages or RPM packages, but for Kubernetes apps. Argo CD can process all of them and map them to what are called apps out in Kubernetes. And so it will grab the code out of GitHub, and then it will sync it to Kubernetes, and which actually causes your application to stand up and run. How does that look like when it's fully deployed? So you basically store the project in GitHub. You have Argo CD running in at least one of your clusters, and then by issuing various sync commands, you can also build in automatic synchronization using GitHub Actions. You are able to then make any change cause a basically will then be applied and and then blasted out to whichever Kubernetes cluster you're syncing with. So this has been a whirlwind tour, but what you get is when you follow these steps, you can now put together a full stack. So we have, and we don't have all the layers here because we're just building the base, but we've got Kubernetes, of course. in this particular, I'm going to demo this in a second. We're using EKS, which is the Amazon managed Kubernetes. We use GitHub for our to store our code. We use Argo CD to implement GitOps to map it to Kubernetes clusters, and then we have the management and storage layers. So we have our observability, we have our ClickHouse operator, and then we have ClickHouse with Zookeeper, and then just to make things fun, I've thrown in Cloud Beaver, which is a nice cloud-based SQL editor that is a containerized version of dbeaver. So that's the stack. This sounded complicated, but when you actually come to do it, it's pretty easy to apply. Let me just demonstrate. So let's go ahead and go out to, I'm now out in Amazon in this screen that I'm showing, and let's have a look at what's going on in my namespace. So I have a namespace called CH, and I'm looking for pods. Pods are running containers, which in turn are one or more running processes in Kubernetes. There's nothing out there. What I'm going to go ahead and do is I'm going to actually bring up the entire stack using Argo CD. So I've got Argo CD installed, and let's see what this looks like. So I'm in this, this is actually a demo project, which you're free to use. Let's go look at the application, at how it's put together. So we'll just pick, I talked about these apps. Let's just pick one. So we're going to go to ClickHouse, and we look at this application, and it's really got, it's a manifest, and it's just, here it is, whoops. So this is the manifest that defines a ClickHouse cluster. So, and this shows various, things like, hey, what version do we want to use? How many shards do we want to have? How many replicas, so on and so forth. It's all defined in about 49 lines of YAML, which is really not bad. So very simple. As we look at the apps in here, they have different ways of installing. So for example, Prometheus installs through Helm. Zookeeper we're doing through a manifest. Cloud Beaver we're doing through a manifest. Grafana you can install with an operator, so on and so forth. So each of these is defined, and now what we're going to do is we're just going to tell Argo CD to bring them up. So here's Argo CD. So Argo CD also has a handy command line tool. Let's go ahead and list our apps. So there we go. Nothing running right now. Let's run a script, which is just going to bring the whole thing up from soup to nuts. Show you what's in the script. These are the commands. So we're going to tell Argo CD where each of these applications is located. And we give a repo, we give a path within the repo, we give a destination Kubernetes that we're going to map to. And then that's the app create, and then we do an app sync, which tells Argo CD, hey, go ahead and actually install this. You know that it's there. Let's go ahead and install it. So let's run that script, and it's going to just as soon as I press enter, you can see these commands, boom, 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 they're running. And now we're just going to see as it's going through the sync operation, we can see a bunch of stuff going on. And we can already see out in the, in the stack, we can already see these, see these things coming up. What we'll see is it will take a little bit of time for these to come up. For example, this is a ClickHouse instance that's coming up. Let's see what we can also look at the. We'll just Control C out it. Let's just see what Argo CD thinks is going out there. So this is Argo CD's view of the world, and it actually tells us that, hey, these applications, not only are they created, so ClickHouse down to Zookeeper, but they are fully synced. And this progressing means the sync process is still in process. Some of these where it says healthy, they're already up and running. But for example, Grafana is still coming up, Prometheus still coming up. Zookeeper stuff. Let's have a look. Let's go ahead and and see how our pods are doing. Okay, so we've got a ClickHouse server coming up here. Let's go ahead and just go to that server. So there was nothing in this namespace. I brought up the full stack. What I'm going to do right now is I'm actually going to go ahead and log into that. So we'll go ahead and do what's called kubectl exec command, which means we can go to the pod and actually look around and see what it's doing. So okay, so we're now in the pod, which is running. This is the running container. If we do a PS, well, actually we don't see ClickHouse, but if we do ClickHouse client, for those of you who are ClickHouse fans, you can see that we are logged in, and actually we're using ClickHouse server version 22.3, which is an old version, and we'll get to that in just a second. But this is a fully, so we can do show databases, for example. So there's our databases, select one, we can run queries. This is a fully functioning ClickHouse server. And in fact, by the time we get out, we probably have both of them up and running, and there they are. So the entire stack is now up and running. So this is basically illustrates how you can bring this whole thing up at once. One other thing I'd like to demo very briefly is we can actually change it. So let's exit. And if we go in, I've got this, this is all, I'm working out of Git here. I'm in my, sort of working on this Argo CD examples project. And let's just do Git status. I've actually made a change here, and you'll see this in a second. Let's go ahead and diff it. So what I've done is I've actually changed the image, because this was actually a typo. It shouldn't have been this old image when we set up the example. It should be the new one. What I'd like to do is actually go ahead and update these my servers. So instead of actually just submitting this directly, what I'm going to do is I'm going to say, so I'm going to just go ahead and add. So go ahead and add that file to stage it to check in. Now what I'm going to go do is I'm going to commit it. And I'm going to push to, when I get the right number of M's, I'm going to now push to GitHub. And I'm going to go to, so I'm git push origin main. Up it goes. So I have just changed this in out in GitHub. Now what I want to do is I actually need to get Argo CD to sync this for me. So I'm going to say Argo CD apps for app list. There we go. And ClickHouse is the name of my app. So I'm going to say Argo CD app sync ClickHouse. Okay, so let's go ahead and do this. And what we'll see is that in due time, what will happen is once this Argo CD picks up this change I've made, we should then see the the synchronization occurring. Now, I think what's happened is it's actually done the sync already. That's why it shows as healthy. What's happening though in the background is we will, if we go look at our pods, we will in due time, oops, there we go. What will eventually happen is we will see this Argos, the operator will wake up and will notice that, hey, the version has changed. It will actually terminate the pod, bring up a new pod with the new version, and basically that's how the upgrade works. It takes a few minutes because it has to allocate background VMs to do this. So I'm not going to wait, but that's basically how this works. So what you're seeing me doing is actually doing a database upgrade through GitHub. This is a really powerful way to develop apps, and is the reason why this custom approach works, because a relatively small team can automate everything. They can store it in GitHub and we can basically keep this, basically keep this stuff in sync, and also incrementally improve it without getting confused about what we're doing. It's a really powerful way to develop applications. So with that, we can go back to the demo. So these are just some best practices that we've seen very consistently. Build on managed Kubernetes. We talked about that, down to picking the GitOps app implementation. I'm using Argo CD in this case, but I would say an even larger number of our customers are using Terraform, from soup to nuts, everything to down to actually applying schema into ClickHouse. That's another way that you can approach it. Argo CD, of course, does it as well. One important point is that by developing the applications in this way, you're not precluding using cloud services when it's appropriate. The stack that I developed didn't include Kafka. In fact, many of our customers they might build the application, the reporting stack, might be completely local, but they actually might use a cloud version of Kafka, like OzMSK or Confluent. So you don't have to make that choice, and you can go back and forth. So just a little bit about how we help enable this model of building these modern analytic stacks and allow you to keep the data on-prem, to meet these additional requirements and operate it inexpensively or cost efficiently at large scale. Here's some of the things that we can do. So we have the Altinity cloud platform for ClickHouse, and one of the cool features of it is if you're running the stack in Kubernetes, we can actually manage the ClickHouse part for you. We have customers that run everything on Kubernetes, but they leave the actual management of ClickHouse itself to us. We give them a cloud management plane. It is connected to securely to the Kubernetes cluster. It's very simple to set up the connection. You just run this a connector app, which then registers with Altinity.cloud, and boom, you're now able to manage ClickHouse. Another thing we do is provide software. You've seen a few of them, like the Altinity Kubernetes operator that's used in thousands of installations worldwide. Altinity stable builds. These are builds that are with 3-year maintenance tail and certified for production use, all the way down to ClickHouse backup. We manage the Vertimedia Grafana plugin, which, as I mentioned, has 11 million downloads, and Tableau connector, among others. And then finally, we have services. So, getting these things to work, if you're not familiar with it, is very helpful to have somebody who knows their way around it. We know ClickHouse as well as anybody in the world, and we're for sure the best people on Kubernetes. We've been doing it for years, and we can help you with proof of concept. And what we're doing is building blueprints like the one I just showed you to help bring these stacks up more efficiently. So that brings us to the blueprint. Here's how to get started with it. You can just clone the examples that I showed you, and you can go run it yourself. It's not complete. I will tell you, we're still doing some work to get one of the things we really want to do is have, for example, the Grafana dashboards just come up automatically. We're working on code this week. It should be fixed in a few days, but this will just continue to get better. But try it out. It really shows the power of Argo CD. And in fact, the projects that went into the stack are listed here. You can read them off the slides. So with that, we're done. I'd like to thank you for listening in, and be delighted to answer any questions about this. If you haven't used Kubernetes before, it can seem a little bit intimidating, but in fact, this is a very, very powerful way to build these stacks. And we see this widely used. This modern analytic stack that I've used is widely used. And people, of course, still use, are using cloud services as well. So I hope this talk has given you hints about the trade-offs between them, how to get the best deal for your, for your cloud analytics service, or how to build it yourself and then get an even better deal, but for specific applications. So that's it. thanks again, and I'll hang around for a couple minutes to answer questions, but feel free to contact us at any time through the website. We'd love to talk to you. This is what we do, and we're happy to help you. Oh, all right. You're most welcome. Great to see you again. Hope this was a good talk. This is Ari Valtanen sent a thanks. So good. Well, I think we don't have questions queuing up. I hope this was helpful. Look forward to talking to you soon, and we'll go ahead and close the webinar for today. Thank you very much. Have a great day.